All right, welcome. Have you ever stopped to think about the invisible power that's running literally everything around you, from your phone to the lights in your city? Well, today, we're going to pull back the curtain on that hidden rhythm. We're talking about alternating current circuits and how they really work. Let's jump in. It might seem super complex, but the entire AC power grid really just boils down to a few key components and some pretty straightforward principles. So over the next few minutes, we're going to break it all down, and I think you'll be surprised at how it all clicks into place. So, to really get a handle on AC circuits, we first need to meet the three main characters in our story. I want you to think of them as these fundamental building blocks, and each one has its own totally unique personality and a special job to do. Okay, first up, we've got the resistor. This is our steady, predictable friend. Then you've got the inductor, who's kind of stubborn, It really doesn't like change. And finally, the capacitor. This is the eager one. It acts super fast. So let's see how each of them actually behaves inside a circuit. The real secret to understanding these components, it all comes down to the relationship between voltage and current. It's kind of like a dance, and each of our three characters has its own signature moves. The resistor? It keeps things super simple. It's the steady one, remember? So, in a circuit with just a resistor, the voltage and current are perfectly in sync. They rise together, they fall together, they hit their peaks at the exact same time. No drama. And what's so cool about this slide is you can see it perfectly. On the left, you see those two waves, voltage and current, just sitting right on top of each other. And over on the right, that diagram with the arrows, it's showing the exact same thing. Both arrows are pointing in the same direction. They are perfectly in phase. All right, next up is the inductor, our stubborn character. An inductor is basically just a coil of wire, and its whole deal is that it resists any change in the current flowing through it. And that resistance to change, it causes a delay. It makes the current lag behind the voltage. So why does it do that? Well, it actually takes time and energy to build up a magnetic field around that coil as the current starts to flow. It's that initial effort that puts the current a full 90 degrees or a quarter of a cycle behind the voltage that's trying to push it. And this visual just shows that delay so well. You see how the current wave is shifted over to the right? It's lagging. Now, a fantastic way to remember this is the little phrase, Eli the Iceman. For an inductor, that's L. The voltage, E, comes before the current, I. So E-L-I, Eli. And finally, we have the capacitor, the eager one. And it is the complete opposite of the inductor. In this case, the current actually gets a head start. It leads the voltage by 90 degrees. And it actually makes perfect sense when you think about it. For a capacitor to build up voltage, it has to store charge first, right? And the flow of that charge is the current. So the current has to happen first. And that, of course, brings us to the second half of our phrase, ice. In a capacitor, C, the current, I, comes before the voltage, E. Eli the Iceman. Trust me, this little trick is an absolute game changer for keeping this straight. I mean, just look at this. The current waveform is shifted to the left, which shows it's leading the charge. And the diagram on the right confirms it. The current arrow is a full 90 degrees ahead of the voltage. That is ice in action, right there. Okay, so we've met all our individual characters, but what happens when we put all three of them together in the same circuit, forced to work side by side? Well, this is where the real drama starts. So in what we call an RLC series circuit, the exact same current has to flow through the resistor, then the inductor, and then the capacitor. This forces our three characters to interact, and their totally opposite personalities create this kind of electrical tug-of-war. This diagram just shows that battle perfectly. The inductor's effect, VL, is pulling the voltage straight up. Meanwhile, the capacitor's effect, VC, is pulling it straight down. They are in direct opposition, a full 180 degrees apart, pulling in completely opposite directions. Now, this combined opposition from all three parts is called impedance, and we use the letter Z for it. You can basically think of it as the grand total of the resistor's simple resistance plus whatever the net result is of that inductor-capacitor tug-of-war. The final outcome really just depends on which one pulls harder. But what if neither one wins? What happens if their forces are perfectly, absolutely balanced? Well, this leads us to this really special, almost magical condition in electronics called resonance.
Just think about that for a second. If the inductor is pulling up with the exact same strength that the capacitor is pulling down, what's the net result going to be?
The answer is they completely cancel each other out. It's a wash. This perfect balance is what we call series resonance, and it only happens at one very, very specific frequency, where the opposition from the inductor, we call that its inductive reactance, perfectly matches the opposition from the capacitor. This graph right here is really the hero shot of our whole story. You can see the inductor's opposition going up with frequency, while the capacitor's opposition is going down. And at one exact point, that's the resonant frequency, FR, they cross. In that one sweet spot, the circuit acts as if the inductor and capacitor aren't even there. So what's the big deal? What actually happens here? Well, with those two fighting forces totally out of the picture, the only thing left pushing back against the current is our good old resistor. That means the circuit's total opposition, its impedance, just plummets to the absolute minimum. And when there's almost no opposition, the current just skyrockets to its maximum possible value. It's exactly like pushing someone on a swing. You give that little push at just the right moment, and you get this huge, powerful result. Now, this might seem like just some neat electrical trick, but this principle of resonance is the secret behind so many technologies we use every single day. Let's take a classic radio, for example. Okay, so when you tune a radio, you are literally hunting for resonance. Your antenna is getting hit with signals from every station all at once. When you turn that knob, you're actually changing the capacitance in an RLC circuit inside, and that changes its specific resonant frequency. When that frequency perfectly matches the station you want to listen to, bam, its signal surges through the circuit, and all the other signals are ignored. You've just resonated with your favorite station. And really, the key takeaway here is that resonance isn't just about electronics. It's a fundamental principle of physics. We see it in the vibration of a guitar string, the swaying of a bridge in the wind, even the way a microwave heats up your food. It's just this powerful reminder of how small, perfectly timed inputs can create these extraordinary results. It really makes you wonder, where else in our world is this hidden rhythm at play?